in Unit 3. It's called That Really Grinds My Gears. It says, a gem cannot be polished without friction, nor a man perfected without trials. Lucius Annus Seneca is a famous Roman emperor. So, the learning goals are that students will be able to describe the effect of friction on the net force, describe the magnitude and direction of the frictional force, distinguish between kinetic and static friction, and describe how a ramp affects the forces acting on a block. So, first of all, what we already know. We already know that free body diagrams illustrate all the forces acting on an object. Okay, if it's not on a free body diagram, it's because it's not acting on an object or you forgot about it. It says a net force can accelerate an object. That's that F net equals ma. F net equals ma. And we also know that friction acts against the applied force, specifically against the direction of motion. So, what we learned in the lab, we learned that friction opposes the motion of an object. When the object was pulled this way, sometimes it didn't move. We also know that the surface of both the object and the surface will affect friction. So, for example, if this is felt, there's more friction than if this thing was some sort of plastic. We also know that friction can keep an object from moving. Now, friction will always oppose the motion of an object. So if I'm attempting to move the object this way, friction is going to act this way. If I'm not, if the boulder is trying to move this way, then friction will act the other way. Friction always opposes the motion of an object. Friction is due to surface irregularity. Okay, even the most smooth surface, when you look at it on a microscopic level, has surface imperfections. Those surface imperfections actually result in two objects that kind of collide with one another on an atomic level. So friction is the resistance force caused by the surface interaction between two objects. And this is going to become important when we talk about electricity, because we'll describe the interaction between these electrons that way. Now, applications of friction. Friction is necessary. Now, there are lots of times when we want to reduce friction, like when we're talking about an engine, and you're trying to reduce the friction, so you're trying to reduce the wear on an engine, or you're trying to reduce the friction between the tires and the road so you get good gas mileage. But there are lots of reasons why we need friction. One, keeping warm. You can take your hands, clap them together, rub them together, and you can warm your hands up. Any sort of acceleration requires friction. Okay, have you ever seen this? If you've ever tried to see a car speed up or slow down whenever it's icy, you need friction in order to change direction, change motion, speed up, slow down. Tires need friction, so they want to have the right amount. They don't want to have too much, they don't want to have too little. Starting a fire, rubbing two sticks together generates heat, which allows you to produce a flame. Air resistance is an example of friction. So you want to have friction in order to make things work, but sometimes you want to reduce it. There are two types of friction. The first one is kinetic, the second one is static. Kinetic friction, the term kinetic itself means moving. So whenever you have kinetic friction, it's the friction that opposes motion. Now, static friction, static means at rest. So whenever you see static friction, it's the friction that keeps an object not moving. So you see an example, you see this cartoon character pushing on a box, but the box isn't moving. Because of static friction is keeping it together, or keeping it in place. Now, static friction is always greater than kinetic friction for the same surfaces. And the reason why is Newton's first law. If you were to look at objects at rest, tend to stay at rest, okay, because they've got those repulsive forces ready to go. So static friction is always going to be greater than kinetic friction for the same surface. So you look at this calculation right here. This is the friction calculation. It says Fs, okay, and specifically that means static frictional force is equal to this mu term. This is like a mu, or you can think of it as like a weird upside down N. I like to think of it as a U with this kind of tail right here. That's the Greek letter mu. And then you see the sub S again indicating static, and then you see normal force right here. Now know that this is the equation for the static frictional force calculation, but if you were to just switch out this S with a K, it would actually be the same formula for the kinetic friction calculation. So the static friction is equal to something called the coefficient of friction. That's this mu term. Okay, what that is that's the ratio of the frictional and normal force, and that's a measure of how much friction will occur. So it's like the what are the surfaces ratio. Do you have smooth surfaces against each other? Do you have coarse surfaces like sandpaper against each other? And then finally you have the normal force. The normal force we've already talked about is the force that's perpendicular to the surface an object rests on. Generally for a flat surface it's equal to the gravitational force. So So you see an example. It says a 60 kilogram person jumping out of an airplane reaches a constant terminal velocity at a height of 2,000 meters. Determine the frictional force caused by air resistance. So if you were to look at this, we have a 60 kilogram person. They're going to have a gravitational force. The gravitational force we can calculate using the formula Fg equals mg. I have the person's mass. I know that gravity is 9.8. If I know those things, then I can go ahead and I can calculate the gravitational force by doing 60 times 9.8. And 60 times 9.8 gives us a frictional force of a gravitational force of 588 newtons. 588 newtons. Now, because they reach terminal velocity, that means it's a constant velocity. Constant velocity means no acceleration, so there must be an upward force that is the exact same force. Now, it can't be the normal force because he's not on the surface. So instead, we call this the frictional force. It's opposing his motion. That frictional force has got to be equal to 588 as well. Now, if you had to describe this frictional force, it would be described as Fk. The reason why is the man is moving, so you have a kinetic frictional force. Next, we have the proficient level question. It says a 2 kilogram box is pushed along a level surface with a force of 50 newtons, resulting in an acceleration of 5 meters per second squared. Draw a free body diagram with the magnitude of all forces labeled. So I'm going to have my free body diagram up here because I'm going to have to do some math. I know there's going to be a force up. I know there's going to be a force down because it's a box on a level surface. So I'm going to start off by calculating the weight of this particular box. Fg is equal to mg, or 2 times 9.8, which is going to give me a gravitational force of 19.6. Because the box is not moving, we can also say that there is a normal force. It's not moving up or down. There's a normal force of 19.6 newtons. So now we need to look at the forces left and right. The next thing you see an applied force. Okay, he's pushing with a force of 50 newtons. So I can say that the applied force is equal to 50 newtons. But the last thing that I need to look at is I'm trying to find the value of the frictional force. And what I can do is I can look at the acceleration of the object. Okay, I can say that F net, or the sum of all the forces, is equal to the mass times the acceleration. Well, the mass we have is 2. The acceleration we have is 5, so the net force is going to be 10 newtons. So if I have a force, these 19.6 numbers are going to cancel each other out. So these numbers are going to cancel each other out. So really, the net force is a combination of the applied force and the frictional force. If the net force is 10 newtons, that must mean the difference between the applied force and the frictional force has to be 10 newtons. So what I can say is the applied force minus the frictional force, those colors don't match very well, is equal to the net force. Or 10 is equal to 50 minus FF, which of course makes the frictional force 40 newtons. This Master A3, it says a 1,000 kilogram car moving down the highway requires 500 newtons to maintain a constant 30 meter per second velocity. Because it's a constant velocity right here, we know that the frictional force is going to equal to the applied force, and we're going to have a frictional force of 500 newtons. And specifically, we know that this is going to be a kinetic frictional force because the object is moving. Determine the coefficient of friction, so I'm looking for the mu k term, between the tires and the road at this velocity. So the last thing that I need to know is I need to know the normal force. Well, remember, the normal force for a flat surface is equal to the weight, and the weight is equal to mass times gravity. So because of that, I can say that the normal force is equal to 1,000 times 9.8, or 9,800. At this point, you have your normal force, and you have your frictional force, so you can solve for the coefficient of kinetic friction using the equation Fk is equal to mu k Fn. Or, in our case, we'd have 500 equals mu k 9,800. Divide both sides by 9,800, and when you do that, you get a frictional value of about 0.005. Next, it says friction can actually be used to hold a block in place. If you have a block and you have a ramp, The general idea is that the block would go down the ramp because it can just slide down the ramp. But friction can actually do its job in holding this block in place. So whenever you have a frictionless ramp, okay, it's just like somebody skiing. They just slide right down. The force actually pulls them down. But on a friction ramp, the friction opposes the motion of the object, and it can actually act in the opposite direction. When we look at the normal force, we originally defined the normal force as being perpendicular to the surface that an object rests on. We said, for an object that's on a straight level surface, that means it's straight up. And the normal force and the gravitational force would cancel each other out. But whenever you have a normal force with a ramp, you'll start to see that even though this value and this value are the same, they no longer cancel each other out because they're pointed in different directions. So the part of this force, the part of this normal force, okay, is not canceled out, and you're left with a force that ends up going down and to the left. So the normal force and gravitational force no longer cancel each other out, leaving a net force that allows a block to slide down a ramp without any sort of push or without any sort of other force. So you see an example. This is the block on the ramp below is motionless. Draw the direction of and correctly label the type of frictional force. So it is motionless. That lets me know that I'm talking about static friction. So the first thing I want to do is I want to draw the gravitational force. Remember, the gravitational force always acts straight down. The next thing I do is I would draw the normal force. The normal force is always perpendicular to the object, the surface the object rests on. Now, if this were the case, if this was the force, the block would slide down and to the right. But we said that it's motionless. So what that means is there must be a frictional force that I'm going to call Fs that is opposing that motion, holding the block in place. Now we have the proficient example. This is draw a free body diagram for the situation below. If you were to look at this, we have an object that has weight, and that weight acts straight down. Now I have two surfaces here. So there's a normal force that's going to be perpendicular to that surface, and there's a normal force that's going to be perpendicular to that surface, and both of them can be considered normal forces. Sometimes we will distinguish and say 1 and 2, sometimes we won't. And finally you have the FG. And finally, for the mastery level question, this says determine the acceleration of a 10 kilogram block down the ramp. So what I want to know is I've got a 30-degree ramp. I want to know what the acceleration of this particular object is. Now this is a tough example and your teacher may choose to exclude it, but let's go through it. You have a mass of 10 kilograms. You have an angle of 30 degrees. So if we're going to look at this, I have a force down here and I have a force up here, and that results in this right here, a triangle, where you have a net force acting down the ramp, and I can say, okay, my net force acting down the ramp, here is my weight. So I can say that the weight of this particular block is 10 times 9.8, or 98 newtons. Now, if I were to look at this side of the triangle, this right here is opposite this angle. I'm going to switch colors so we can see a little better. Opposite this angle right here. Okay, this angle is the same as this angle because of alternate interior angles from geometry. So the angle of this particular triangle is 30 degrees. If that's 30 degrees, then this side of the triangle can be calculated by saying the sine of the weight. So weight times the sine is going to equal that new applied force. So I can say that 98 times the sine of 30 is equal to the applied force. Well, the applied force, or this net force, the sine of 30 is 0.5. So what I can say is that this applied force, if you didn't know that, you could use a calculator. The applied force is now 49 newtons. Not 4.9, but 49 newtons. Now that I have the applied force, the leftover force, I can use the mass of the block, and I can use F net is equal to MA, or 49 is equal to 10A, and the acceleration, divide both sides by 10, would be 4.9 meters per second squared.